Hi everyone. In this video we're going to finish up section 3.2 with just one slide left, and then we're going to move into section 3.3. And so this one thing that's left from section 3.2 is a little bit different than the rest of the chapter and our focus, but it's important for what we do going forward. And so it's about something called a parameter or parameters. And so to preface this, I really should say that so far we've only viewed probability distributions in situations where we can build a table that can view all of the outcomes and then associated probabilities. And so as we talked in previous videos and in class, there's a limit to how many that we can do before a table gets sort of outrageous. But that's not the way that most people view probability distributions. And what they actually do, or where people usually actually view them as, are functions that we sort of usually think of as functions. So like x's and y's, so on and so forth. And in doing that, we can actually view a whole bunch of different probability distributions that look the same or similar, and consider their functional forms. That's going to help us. Okay, so I know I didn't explain that the best, but hopefully that paragraph there says it sort of well. As an example of what I'm talking about, remember the Bernoulli distribution, or a Bernoulli random variable. Okay, so for Bernoulli random variables, there's an associated probability distribution that goes along with that, and it's called a Bernoulli probability distribution. Okay, so it goes along with that Bernoulli random variable, which there's only one success, there's only two choices, success or failure, 0 or 1, so on and so forth. Okay, and that happens with some pre-specified probability. So flipping a coin, heads or tails, that's a Bernoulli random variable. And if it's a fair coin, then the probability that it lands heads is 50%, tails 50%. Okay, and then you have all kinds of different probabilities, anywhere from 0 to 1, that you can do it. So how do we describe a Bernoulli distribution as with a functional form? And we do it in this way. And this has to do with parameters. Okay, so we have the function f, and this is, of course, a piecewise function. And if x is 0, or rather, this is the PMF, remember. So what I'm writing here is the PMF. And so the PMF says that the probability that x is 0 happens with frequency 1 minus alpha. Okay, it turns out that alpha is going to be a parameter, but I'll introduce that in just a second. So 1 minus alpha, probability that x is 0, and then alpha, probability that x is 1, and then everything else is 0. Okay, and alpha, which in this case, alpha is always the probability of success. Because we defined it as such in our piecewise function, alpha can go between 0 and 1. So it can be any real number between 0 and 1. And so that's what I've said over here. And so this is called the Bernoulli probability distribution. But what I've done, in fact, here in this piecewise function is I've specified a whole number of distributions. And it's all based on alpha, which we're going to call a parameter. Okay, and so I get rid of this. Each time I change the alpha value, I get a whole new distribution. So if alpha was 0.5, if we were flipping a coin, fair coin, alpha would be 0.5. If I were doing something else, it might not be 0.5. But each time I change that alpha value, I get a whole new distribution. And so that alpha is called a parameter because it, in more formal language, it parameterizes, that is a word, the distribution. It sort of defines what makes that distribution that specific one. Okay? So it distinguishes one Bernoulli distribution from another. So I could have a Bernoulli distribution with alpha equal to 0.01, or I could have a Bernoulli distribution with alpha equal to 0.95. Okay? And then sort of anywhere in between, and all the way up to 1, all the way down to 0. Okay? So the parameters are going to be important because each of the distributions that we look at are going to have their own parameters. And the parameters describe or distinguish one distribution, one member of the family from another. So I call this the Bernoulli family of distributions because it's really a bunch of them that have the same functional form. Okay, so you can sort of set that aside. It's not really critical for what we're doing right now, but it is important to keep that sort of in the back of your head when we go forward. But really, what we're interested in this section, are expected values. Okay? So this new section, section 3.3, is called expected values. And so what does that mean? Why does it matter to us? So on and so forth. Hopefully I can answer those questions. So first we want to look at the expected value of a random variable. Right? Random variables have a number of properties that are of interest. So I want to know a couple of things about the random variable, or people usually want to know these few things. The most popular one that people are interested in is the mean or expected value of a random variable. So for instance, I could set up a problem where I define some gambling game. Okay? So, you could do this for any sort of scratch off, any of the lottery games. The expected value is really important to us. Okay, so if I have a random variable, which is your winnings for a game, and let me set up a really simple game here. Okay, so if I have a deck of cards, 52 cards, right, and the game is you walk up to me and you select a card out of the 52 cards, and you have to pay $2 to play the game, and you win $20 if you pick an ace out of the game. So the game is to pick one card from 52 from the deck. Okay, so you pick one card from the deck. If it's an ace, you win $20. Other ones, if you pick anything else, you lose, or you win $0. Okay, and you have to pay $2 to play. All right, if I wanted to set up a probability distribution about my random variable and let x, the random variable, be my I want to be sure to define this in the right way. My net earnings, let's say net winnings. net winnings. And so that's winning, what I sort of walk away with from the game after I've played it. And so X has two possible values. I could play the game and lose, and thus my net winnings would be negative $2. Or I could play the game and win, and so my net would be positive $18. Okay? And so what's the probability that each of those happens? Well, there are 48 cards in a 52 card deck that aren't aces, and then there are 4 cards that are. And so that would be my probability distribution there. Okay? And it's probably advantageous for me to know the expected winnings from one play of this game. Okay? And so that might seem weird, this might be helpful, this might not quite be helpful. If I find the expected winnings from one game of this, if it's positive, if my expected winnings are positive, then I know that this is a good game to play. And if my expected earnings are negative, I know it's not necessarily a great game to play. In reality, any game that you play, that you're paying to play, the expected winnings should be negative, okay, or else the person who's in charge of the game is not very smart, okay, because they should hope to win money from putting on the game. So hopefully that made sense. If not, I'll mention this again in the future, and hopefully it'll make sense then. But anyway, so the expected value or mean of a random variable. This tells us where the center of the probability distribution is. So the probability distribution about that random variable, this tells us where the center is. Okay. Again, on something like gambling, hopefully the center of that distribution would be negative. Okay. If it's positive, then that person's going to lose money by putting on the game. If it's negative, you're expected to lose. Okay. If you do this calculation for any game in a casino, they're all going to be negative. And in fact, people have done, and they can tell you if you look online without much trouble, I'm sure you can find what sort of the best games that are completely random to play are, and what you'll lose the least amount on. But anyway, what is a random variable? What is the expected value of a random variable? And this is a formal definition here. Okay, so let X be a discrete random variable, which is what we have, with D possible values. Okay, so I don't know quite how many possible values there are, but I know there are sort of D of them. I don't know it's exactly which of them are which, but I know there are total D. Okay? And a PMF f of X. So I know what my PMF is. Okay? The expected value or mean of the random variable X, denoted by E of X. Okay, so there's a function E that operates on random variables. So I could call it E of X, or I will also often call it mu of X. So mu with a subscript of X, meaning the mean of the random variable X, is the following. Okay, and so hopefully, so what it is it's the sum over all values of the value of the outcome times the probability it happens, and then you sum all of them together. Okay, and so let's look at an example. And this is the example that I've been using throughout section 3.2, and I'm going to have to erase some of my work here, so forgive me. Okay, so the expected value says I'm going to take each value of the outcome, or each outcome value, and that x corresponds to this x. So each outcome, and multiply it by the value of the PMF of that outcome. Okay, so what does that correspond to? This x corresponds to the 0. This f of x corresponds to that 0.05. Okay, and so I do that for every single one, every single outcome. I multiply it and the probability together. So 0 times 0.5, and 1 times 0.1, 2 times 0.15, 3 times 0.25, so on and so forth. You multiply all of them together. That's what this part says to do. And then the capital sigma here is a sum. So you sum them all together. And when you do that, you get this. Okay, so I've written out all of it, where you see I multiplied these two together and got this, and then I did that for all of them. So you multiply them together, and then you add it to the addition there. And so when you add it all up, so on and so forth, you get a number, 3.3. Great. So remember, in this problem, it was Shippensburg Math Department has a computer lab, has 6 different computers in it, and let X represent the number of computers that are taken or are in use. And so what this says is that on average, around 3.3 computers are going to be in use. Okay? And so there are a number of things here that are sort of weird. The first weirdness is that 3.3 is not a possible value here, right? So there are 3.3 computers. Can't happen. But that doesn't mean that you should round it. Okay, so what does it mean in context? It means that on average, around 3.3 computers are going to be in use at a single time. And so that may mean a little bit to you, that may mean a lot to you. It depends on the context of the problem. In this problem, it's okay, around a little over half of the computers are going to be in use at a time. And so that may change your decision about whether or not you want to go to the computer lab to try to work in there, so on and so forth. Okay, but the biggest sort of issue that people have often with these, when you're learning about expected values or means of data or random variables, so on and so forth, is that it's not a possible outcome. And so the thing that people will try to do the most often is round it. So you'll try to say you'll round it, and then you'll say the mean is 3. But I'm here to say do not round expected values. Never, ever, ever round expected values. Okay? The mean does not have to be a possible value of our experiment. Okay? So for instance, when people tell you the average number of children in a household, the average used to be around 2.4. Clearly, you can't have 2.4 children, okay? But you do not round it to say 2. You say 2.4. Okay? So never, whether you agree or not, just never round expected values. Okay? Expected values tell us the center of the distribution. Okay, so That's expected values. And so here is your turn. I give an example here. It's from the book. Okay. You have, remember that this p of x is the same as f of x. It's just the same as the probability that x equals x. Okay. The book just calls it something different. All right. I give you the PMF as a table, and I want you to find the expected value of x.